Adding vectors is very straightforward. 2 newtons up plus another 2 newtons up gives you 4 newtons up. 2 newtons up plus 2 newtons down gives you nothing. Multiplying vectors is a little more intricate. You have to figure out what you need the vectors to do and why you need to be multiplying them in the first place. There are 2 kinds of vector multiplication: the dot product, where you multiply the parallel bits, and the cross product, where you multiply the perpendicular bits. For now, let's take a look at the dot product. Our example for the dot product is the example of work. Work is a change in energy. In this case, you're changing the potential energy of that set of boxes. And on the ground, they didn't have the potential to fall or the potential to go anywhere in the truck. Lift them up into the truck, they'll have the potential to fall and the potential to be driven away to your new house. Here's your mover. It is his job to do the work. Work is the dot product of force vector and the displacement vector, F dot D. The displacement in this case is the distance you want to go up the ramp. There, you need to displace those boxes from here to here, this-a-way. So, to take the dot product, you need to find the force in the right direction. Which direction should you pull or push in? Take a look at the picture and tell me which is the best direction for that mover to pull those boxes in. Let's see. Is it this one? Right here? No? Huh. Well, which direction is the least helpful? Let's see. Which direction is the most helpful? That looks good. Nope, we've passed it. What about this? Well, this is definitely useless. If the mover pushes the boxes this way, perpendicular to the ramp, they won't go up the ramp at all. He can pick them up, he can put them down. He can pick them up, he can put them down. He won't actually be doing his job of loading the boxes into the truck. Which is the most helpful? Well, this way. Right up the ramp. Look at the direction of his arms. You can see they're going this way. That's the right direction to pull if he actually wants to get the work done. Question: can there be negative work? Sure. Let go, or push this way. The boxes will fall off the dolly, slide down the ramp, come crashing down, and that will definitely be a negative result for the worker. Which direction should you push in? Conclusion? You should push this way, right up the ramp. Compare the directions of those vectors. The dot product is the case where you multiply the parallel bits of the vectors, because that's the right direction in which the problem, well, works. Check. Are your vectors pointing in the same direction? If they are, perfect. F times D, you're done. Are the vectors pointing entirely in the wrong direction? That is, orthogonally, perpendicularly to each other, so that absolutely no part of the red vector is in any way going in the same direction as the purple vector. In which case, the dot product is 0. There are no parallel bits to multiply, aka you are going in the wrong direction, aka you are not doing your work. You're making a Starbucks run. Answer: 0. Try again. What if the vectors are mostly pointing the same direction, but not all the way? We're supposed to be going this way. Well, some of the red vector is going that way, most of it, everything but this bit over here. I wouldn't say that's 0 work. Some work is clearly being done. Pull this way, and you'll get up the ramp eventually. How much work will you do? Let's figure out a formula. Let's find a formula for those parallel bits. How much of F is parallel to D? That's the question. When we find it, we'll multiply it, we'll be done. F has parallel and perpendicular components. We can go this way as the crow flies, or we can go this way up the D, up the ramp, and then go this way, and we'll still have arrived at the same vector. Let's see, we were going to go this way, parallel to D, or this way, perpendicular to D. Aha! There we have it. F is as the crow flies. These two components are our driving directions. Got a nice little right triangle here to bust out some SOHCAHTOA. Look, it comes at an angle of theta, the angle between F and D when they are drawn tail to tail in your physics notebook or your math notebook. Note that this is not a photograph of the problem. This looks nothing like the mover. You have to draw this yourself. So, label the sides of your right triangle, label it opposite, label adjacent, and press play when you're ready. Sine is opposite over adjacent. multiply both sides by f. The opposite side should be f sine theta. Where's your opposite side on your triangle? If you've located it over here, you're in great shape. This side must be f sine theta. That is the perpendicular component of f. The part of f that's going off in the wrong direction entirely must be f sine theta. We were looking for the parallel component. The parallel component is the adjacent side on your right triangle over here. Adjacent goes with cosine. Multiply both sides by f. Write down the formula for the parallel component when you have it. Press play when you're ready. If you got the parallel component of f cosine theta, you are good to go. F goes in mostly the right direction. F cosine theta goes in the right direction. F sine theta goes in the wrong direction. Our job was to find the parallel bits and multiply them. The parallel part of f, the part that goes in the right direction, is f cosine theta. Now, multiply by d, f d cosine theta. Find the parallel component, check, multiply, check. What do we get? F d cosine theta. Write it down, put a box around it. The formula for the dot product in polar form. Take your two vectors f and d, multiply them. If f and d are in the same direction, you're done. Cosine 0 is 1. If f and d are perpendicular to each other, you're also done. The answer is 0, because the cosine of 90 degrees is 0. If they're not completely parallel or completely perpendicular, fd cosine theta will give you the percentage of f that's going in the right direction to be multiplied with d. Done. Please note that the dot product is a scalar. The vector direction goes away here. We are finding work, which is a change in energy. And you either have energy or you don't have energy. You don't have energy at north-northwest at point north like a pirate. Review. Let's take a look at the dot product here. F and D. Check them. Are they in the right direction? If so, multiply them. Are they in the wrong direction? If so, you're done. 0. Are they mostly in the right direction, kind of with some parallel bits? Bust out your formula. Draw the picture tail to tail, FD cosine theta. Application questions. As you try to get your work done, pulling as hard as you can. What's the dot product of two orthogonal vectors? Pause, write down the answer, press play when you're ready. If you said 0, you understand what's going on. Dot product is multiplying the parallel bits. There are no parallel bits of two orthogonal vectors. Next question. In what direction should you pull to do the most work? Think about this. Think about it in a practical context. Write down your answer. Press play when you're ready. If you said you should pull parallel to the direction you want to go, that's good advice in theory. It's certainly true. You should pull as close to the right direction as you can. If you can't pull perfectly parallel to the direction you want to go, or if it's not comfortable to pull in the direction you want to go, because frankly it's better for your arms to pull a little bit this way, just a few degrees up, in that case, you should pull as close to parallel as possible. The closer you are to parallel, the bigger your dot product is going to be. Related question. What direction should you pull in to do the least work? That is, to make your dot product the smallest. Think about it, prepare to be argued with, write your answer down, press play when you're ready. This is a tough one. How do we define the least amount of work, given that work is a scalar? If you defined the least work as 0 work, then you would pull perpendicular to the direction you want to go in. That is, pull this tug-of-war rope straight up, it will do your teammates no good whatsoever. However, if you define the least work as negative work, then you wouldn't be pulling parallel in the right direction, you would be pulling anti-parallel in the wrong direction entirely. You could consider the least work not as pulling straight up to do nobody any good, but actually switching to the other side and pulling to assist the other team. Not only are you not doing work for your team, you're actively doing work for the other team. The question of the least work is going to be a subjective one that's situational. In which case would you either fail to do the most work or actively do the most harm? This is where anti-parallel comes in to hang out with parallel and perpendicular. There is no direction that you can pull in that you can't now take the dot product. Find the part of the first vector that is in the same direction, parallel or anti-parallel, with the second, and multiply it. F d cosine theta.